In this short video, I am going to work on problem 15 of 18 in lab number 4. This is a problem about some of the assumptions and conditions that are required for regression to provide us with insights about how two variables relate to one another. So let me share my screen with you and visualize the problem. In this problem, you have a student or a recently hired worker who is analyzing credit card information from customers for a bank. The researcher selects 20 customers at random and tries to identify if there's a relationship between those customers' March charges and February charges. Since February comes before March, February is going to be the explanatory factor that follows the horizontal axis, and March is going to be the factor being explained or predicted by February. So it's going to be the Y factor on the vertical axis. And what the researcher found when he or she ran this regression is an R-square of 91%. So I'm going to open the data. You can see that there's a data table for the 20 total charges in February and in March. And I'm going to open that particular transaction in Statcrunch, which leads me to now have to go and share the regression screen. So here you have 20 transactions in February and 20 in March. Over here, I'm going to put the assumptions that are necessary for a valid regression analysis. And the assumptions that are valid for regression analysis are several. One is that X and Y must be quantitative variables. In other words, they cannot be categorical variables. They can't be words. They have to be amounts. And in this case, notice how February and March are in dollars, so that assumption is satisfied. We also have the linearity assumption. The linearity assumption says that when we look at a scatter plot between X and Y, the form of the data should be approximately linear. The data doesn't have to look like a string of that fits perfectly onto a linear path. It could be a very look like cotton candy, or it could have a shape that has bulk to it, but the bulk should be linear. It's almost like those floating devices that look like noodles at swimming pools. They can't be bent, they have to be straight. That's what the linearity assumption holds. Otherwise, building a linear model for data that isn't linear is like trying to fit a square peg in a round hole. It's just not a good fit, and it's not going to lead to what the statistic R-square measures, which is the goodness of fit of the data to this linearity assumption. And to get an R-square of 91% indicates that this data should look linear. To confirm this, I'm going to graph a scatter plot of the data. So this is how you check on the linearity assumption. You set February to be the X variable and March to be the predicted variable Y, and you compute. And you look at the scatter plot, and you'll see an image that kind of looks a little bent, actually. It looks a little not linear. But, you know, if we activate in the options a overlay of a linear function, a line of best fit, a regression line, we'll see that nearly all the data points are close to a linear path. So the linearity assumption is not badly misrepresented by this data. However, I'm noticing something else going on. I'm noticing that there's these two data points out here that are really, really vastly different from the other data points in terms of amounts of money charged on a credit card by an individual. This is quite exaggerated amounts of money to be charging month by month by individuals. So I may be concerned with a violation of something else, something called the outlier condition. So we want no outliers in the presentation of the data. To check for outliers, I'm going to look for a graph I learned about in chapter 3, where we learned about the detection of outliers in a box plot. So I'm going to take both February and March, and I'm going to use fences to identify outliers. And when I compute, I actually notice that there are definitely 2 outliers, and there may be possibly a third one. However, notice that it's only the X factor that is an outlier. The Y factor is not an outlier in row number 6. So I'm actually not going to consider that an outlier. I'm going to therefore identify 2 outliers. The 2 outliers are in row 4 and in row 16 of the data. Okay, so row 4 and row 16 are outliers. Row 4 and 16. So I'm going to keep in mind that that those 2 data points may be violating the outlier condition of the assumptions of a linear regression model. The last thing to check for in a linear regression model is the equal spread condition. So we want the data to show equal spread around the regression line. And based on the scatter plot that we drew earlier, the data points don't seem that badly off the mark with respect to how far the data points are from the red line. There might be a little bit more spread on the high end in terms of variability of the data points than on the low end. And that might be an issue, that the equal spread condition may be violated, but I'm going to visually just go ahead and proceed with a regression for this analysis. And I'm going to say that this assumption is okay. Just like the linearity assumption is okay, just like the quantitative variables assumption is okay. So the only condition that I'm worried about is going to be the condition for outliers. And I'm going to remember that it's row 4 and row 16 that are problematic. Upon doing the analysis, I'm going to run a regression with all the data points, where February is used to predict March by using stat, regression, simple linear, and selecting X and Y appropriately. And I'm going to notice that there's a 91% fit between February and March according to this regression line that we see here. So an R-square of 91% indicates that there's a 91% variability of March being explained by X, which would make this a very strong linear model, a very good predictive model of behavior in March by consumers using credit cards from consumers using credit cards in February. So February is telling us something really valuable, it contains valuable information about March in this model. The model here in line 3 of the summary regression output. So we have a very strong correlation and a very strong indication that when people spend a lot of money in February, they're likely to spend a lot of money in March and vice versa. So the question is this a truly valid model? Well, in a way, it's a good model, but we have concerns about rows 4 and 16. So what I should do is run a second regression without points 4 and 16 in the mix, only having 18 data points, and see if the R-square remains really similar. If the R-square remains really similar to the original model, then the outliers are not influencing, the potential outliers are not influencing the regression results. But what we see is that when we take off those 2 data points, the 2 data points from the earlier regression, let me put them side by side to compare them, the 2 results. The R-square goes from 91% to 28%. By taking out the 2 data points, notice how the sample size went from 20 to 18. And so there is a large discrepancy in how well the model fits the data, how well February explains March. So as a result, we would say that if we go back to the problem at hand, the best result is that there are two outliers, and that the two outliers inflate our square. Without those two data points, the R square goes from X explaining 91% of the variability of Y, February explaining 91% of March, to February only explaining 28% of March. And so that's how we would answer a question like this, by examining the assumptions and conditions of regression, which are actually reviewed in the publisher video for chapter 4. So let me show you where you can watch the video to check the assumptions and conditions of this particular chapter, and how to look at that. You go to chapter contents, you go to chapter 4, and the video presentation for chapter 4 is right at the top. And then if you actually look at section 410 of the chapter where it says, is the regression reasonable? That's where you go over the 4 assumptions and conditions of the model in question. I thank you for watching this video, and I hope it answers some of your questions about chapter 4 and using regression. And with that in mind, I will stop the video and have a good day.